This lecture is going to be on double integrals using polar coordinates. So in rectangular coordinates, the region R that we were integrating over, we would break up into small rectangles where we have each rectangle has width delta x and length delta y. Well, for polar coordinates, what we want to do is something similar, but these rectangles really look like rectangular sectors here. They look like this. So the picture now looks like we're going to take a region and break it up into little pieces that look like this down here. And you can see it's going to involve the angle here, the angle's changing, and the thickness here, which is a change in the radius, r, or a distance from the origin. So here's a picture in the xy plane where the base is broken up into these regions we're talking about, and you can see how they're formed by coming from the origin. They're little pieces of sectors, really. And the height would come in here. There would be some height involved. And so you would have something on the top. And so you're getting the volume of something where you're integrating over this region down here, telling you what's going on with r and theta. And the height is determined by whatever the z is. So z will be some function of r and theta. In rectangular coordinates, when we had to make up a double integral, what we did was we used the function for our height, and a piece of the area was delta x delta y, or delta y delta x, and we were sum. So this was representing the volume of a small piece where the delta x and delta y is telling us the thickness and width of the piece, and this is giving us the height. And then as we let delta x and delta y get small, the number of pieces get large, the sum turns into a double integral, the height stays there, this function, and then the delta x and delta y become dx and dy. In polar coordinates, what we're going to have is something similar where we have a sum, and we have a height function, and this delta A will be a small piece of a sector, and they get smaller and smaller, and the number of pieces we have will become more and more, and this will approach a double integral in polar coordinates. But before we get too far, we need to understand what's going on with this delta A a little bit better. It's not going to be something as simple as delta x, delta y was over here, and I want to show you what's involved with what this delta A is. So first, I need to remind you that the area of a sector of radius r and interior angle theta is 1/2 theta r squared. So here's a picture. So we have an angle of theta here, the radius is r, and I'm saying the area of this is 1/2 theta r squared. Now notice when theta is 2 pi, that means you get the whole circle. This is just going to be 1/2 2 pi, so pi r squared. So if you remember the area of a circle is pi r squared, it's just because when I put in 2 pi here, I'm getting a pi r squared. Of course, if I wanted half of that, I should get pi here, and it should be, instead of pi r squared, 1/2 pi r squared, and that's exactly what it is. If this is pi, you'll get 1/2 pi r squared because you'll have, if the angle is pi, 1/2 of a circle. In this particular picture, I actually made this 1/5 of a circle. So the area should be pi r squared divided by 5. And what's the angle? The angle is 2 pi over 5. You can see if I take 2 pi over 5, multiply it by a half, I have 1/5 pi r squared. So it is pi r squared over 5 for that area. So we want to use that, and the way we're going to use that is as follows. I want to take a little small sector piece here, and I want to find out what its area is. So that's going to be our delta A. And how am I going to find out what this area is? Well, I'm going to imagine that this is coming from the origin again, because that's the way we are thinking of this. And we have some things here. This is going to be R, and this is going to be a change in R. So this will be R plus delta R for the whole length. That's a little change in R. So I want this to be small, so I'm going to think of it as a delta R, change in R. And similarly, this should be a small angle here, so I can think of that as my delta theta. It's a small change in the angle. So what we want to know is what's the area of this piece? What is delta A? Well, we can use what we talked about up here, the 1/2 theta r squared, because we have a actual sector here going from here to here to here. That's a sector. We can find that area, and we have another one going from here to here to here. So this area here is a sector, and so I can take the big one minus the small one to find out what the area of this piece is. Let's look at that. So delta A is going to be, I take 1/2, that's coming from here. I take the angle, delta theta, and for the big sector, I want to use r plus delta r, and then we want to square that. So r plus delta r squared. And for the smaller one, just going up to here, this part that's not shaded here, this is going to be 1/2 again, the angle delta theta, and then the radius just r squared. So this will be then the area delta A. It's the bigger sector minus the smaller sector. So I can multiply this out. You can see the r squared here when I multiply this out, times delta theta times 1/2 will cancel with this. I will still have a 2r delta r for the middle term times delta theta times 1/2. So that'll be an r delta theta. And I'll have a delta r squared times delta theta times 1/2. Those don't cancel. So this is what I'm left with. Again, this is coming from the middle term, the 2r delta theta times 1/2. And then we have the delta r squared times delta theta times 1/2. That's giving us this term. The other term with an r squared here is 1/2 delta theta r squared, which cancels with this. So the way we want to think of this is that if delta r and delta theta are very, very small, so like 1/1,000,000. So 1/10 to the 6, well, the product of these two would be 1/10 to the 12th. That's fairly small. But that's not nearly as small as this. Because if each of these are 1/10 to the 6th, this would be 1/10 to the 18th. We have three of them. We have delta r times delta r times delta theta. So this is going to be a lot smaller than this. So as delta r and delta theta get smaller and smaller, this becomes smaller quicker. So this is approximately just the first part of this, the r, the delta r, delta theta. And as delta r and delta theta get smaller and smaller, this is going to be a better and better approximation for what delta A is. So we want to think of delta A then as being r, delta theta. Okay, so back what we were saying. So now this delta A that we were just talking about, this is our height function again in our sum. The delta A is some value of r that's inside the region that we're talking about here, inside that piece of the sector. And this is a delta r and a delta theta. So this r delta theta is a delta A that we were just talking about. Now, as things get small here, the delta r and delta theta, the number of pieces get large. This sum becomes a double integral over the region we're looking at. The f is still giving us the height, and now we have an r dr d theta. So an r dr d theta coming from the extra r here, and the delta r and the delta theta. So the thing to keep in mind here is rather than just having a dx dy like we had there, we have an extra r dr d theta when we're integrating. So if I have my height function as z equals f of r theta, and I'm trying to find a volume, I'm going to have to put an r dr d theta there. So that's the way we set up our polar coordinates. So let's look at what we want to do in general. We want to take a function dA here, integrating over a region, and we're going to keep the function there and replace the dA with r dr d theta. So this is telling me limits of integration. Theta is going between two numbers. I'll always have theta on the outside going between two numbers. So this is the angle. I'll have a picture in a second. And r is going to go from, this is going from the curve closest to the origin to the curve furthest from the origin. So here's the setup. Again, what they suggest, at least in some book, on how you do this, and I prefer to do the opposite of what it says. Do this first. Figure out the range on theta. If this is the region, you'll look at the first place theta hits the region to the last place theta hits the region. And I say first place because theta is the angle from the positive x-axis, so you imagine theta going around the x-axis counterclockwise here, starting at 0 and increasing. And this would be the first value you hit, theta equals alpha, to the last value, theta equals beta here. And then we take a line from the origin, fixing theta at some point, at some value between the alpha and the beta here. We fix theta and take a line from the origin. The first curve we hit is the R1 at theta. So R is going to start at R1 at theta, and then it's going to go to R2 at theta. So the integration limits would be from R1 at theta to R2 of theta for the integral with respect to R. So theta would go from alpha to beta, R would go from R1 of theta to R2 of theta. This is the important information. We have in polar coordinates x equals r cosine of theta, y equals r sine of theta, x squared plus y squared equals r squared. So those are the usual polar coordinates. And we have f of xy is equal to f. We have r cosine of theta is x. We have r sine theta is y. And we have x squared plus y squared equals r squared. So dA will be dx dy, dy dx, or r dr d theta for integrating in polar coordinates. And then we set up this integral again. Theta is going from alpha to beta on the outside. And then the inner integral, we have r going from r1 at theta to r2 at theta. So this contains all the information we need. This is representing a rectangle here that we're integrating over in the sense of a rectangular sector, really, because r is going between two numbers and theta is going between two numbers. So this is what it looked like. Not so important. This is the more general situation we're in. We have theta between alpha and beta that we just described. Now here they're using h1 of theta and h2 theta for the limits on theta, and that would give you what we need when we're integrating with respect to r and theta. But part of the point of this is if you're given an integral in terms of x and y, and you want to convert it to an integral involving r and theta, we're going to replace the x with r cosine of theta, the y with r sine of theta, and the dx dy, the dA with r dr d theta. So, and then the limits of integration, whatever you have here, you have to figure out what that region is and rewrite it in terms of r and theta. So let me do some examples. Find the area inside a petal of the rose r equals sine of 4 theta. I am not expecting you to know what something like this looks like. I would give you the graph to go along with it if I were to ask this question. So this is what it looks like. There are 8 petals. The problem is to find the area of one of these. Here you want to find the area of this petal. So we need to figure out where this petal is. What is going on with theta here? So it looks like theta is around 0 here. You might guess pi4, so let's check. When theta equals 0, the sign is 0, so that's starting out at 0. Let's try something in between. If I make the theta equal to pi8, this would be 1. That's the biggest it's going to get. So at pi8, we're out here at the biggest it's going to get. That's the distance from the origin, r. So the largest it's going to be is 1, and that's out here. And then by the time you get to pi4, that's going to be the next time that the sign is 0, because we have 4 times pi4, that'll be pi, and that's going to give you 0 again. So this curve is from theta equals 0 to theta equals pi4. So indeed, theta is going between 0, 0 here, and pi4. So we set this up, putting theta between 0 and pi4. And then we need to see what's happening with r. Well, for each fixed theta, r goes from the origin to the curve. R goes from the origin to the curve. So we're starting at r equals 0 and going all the way out to our curve, which is r equals sine of 4 theta. So the limits of integration are from 0 to sine of 4 theta. Again, r is going from 0, from the origin, to the curve, sine 4 theta. And I have an r here, dr d theta. So why did I do that? That's dA. And we're trying to find the area. So that's a good question here. We're actually area, not volume. Remember, if we integrate 1 dA, we're getting the area. So again, I'm thinking of just doing a volume of this where this is the base and the height is 1. So I'm integrating 1 dA. But dA is r dr d theta. So it's 1 dA, and 1 dA is r dr d theta. So let's evaluate this. I integrate with respect to r first. I'm just going to have r squared over 2 when I integrate r. R is going from 0 to sine of 4 theta. And 0 is going to be 0, but I need to plug this in. I'm going to get sine of 4 theta squared, or sine squared of 4 theta. I went ahead and took the 1/2 out, but I have the sine squared of 4 theta I need to integrate. So how do I integrate that? Well, sine squared is not a completely trivial integral to do. There are different ways we can do this, and there's a simple way because we know the limits of integration here that I won't go into, but in general, when you have sine squared, you need to use one of these identities, this one for sine squared and this one for cosine squared. So I want to replace sine squared of 4 theta with 1 minus cosine of 8 theta over 2. So I'm going to replace this theta here with 4 theta, so this becomes an 8 theta. So sine squared of 4 theta is 1 minus cosine of 8 theta over 2. And I can take out this 1/2 and give me a 1/4 there if I want. So that's where the 1/4 is coming from because I have a 1/2 from this. And that's give me a 1/4 then. And then I'm left with 1 minus cosine of 8 theta. So I need to integrate each of these. This is going to give me theta. I have a cosine of 8 theta there. Now the cosine of 8 theta, when you integrate that, you're going to get sine of 8 theta over 8. So why do I have 32 here? It's because the extra 4 down here, this is 1/4 times this integral. So I have 1/4 times 1. When I integrate that, I get theta, 1/4 theta. I have, again, sine of 8 theta over 8 when I integrate this, but times 1/4, that gives me 1 over 32 times sine of 8 theta. So I want to evaluate that from theta equals 0 to theta equals pi fourths. At pi fourths, we're going to have 0 because 8 theta at pi fourths will be 2 pi, and sine of 2 pi is 0. So this is just going to be 0. And at 0, we have 0. So this part doesn't even come into play. But here we're going to have pi fourths minus 0 when I evaluate it from 0 to pi fourths. So it's going to have pi fourths times 1/4, or pi 16ths. So the answer to this example then is pi 16ths. That's the area of one petal of this rose. So let's do this example next. In this example, we have e to the x squared plus y squared, dy dx, and some region we're integrating over in the xy plane. Now, you can try to integrate this. It would help if you first rewrote it as e to the x squared times e to the y squared, since you add exponents when you multiply e to the x squared times e to the y squared. But then you still have to integrate e to the y squared dy, and that's not an easy integral to do. You're not going to be able to do that. So the idea is instead to use polar coordinates, because in polar coordinates, x squared plus y squared is just r squared, and we're going to have an extra r when we replace this with r dr d theta. And that's going to help us integrate this. So what we need to do is to change to polar coordinates. So this is a second approach we're going to use for doing a double integral that we don't know how to integrate. The first one was to switch the order of integration. This one is to go ahead and switch it to not the dy dx around, but switch it to polar coordinates. Now notice, if I just interchange the order of integration here and put dx dy, that's not going to help because I'm still going to have to integrate e to the x squared, and that's not going to be easy to do. So we want to go ahead and use polar coordinates. And that means I got to look at what region this is to change the order, the limits of integration to polar coordinates. And then I got to switch this with r squared, and then I got to switch this with r dr d theta. So let's see what I did here. Well, let's see. I've already switched the limits of integration. Where did that come from? Well, what is this? X is going from 0 to 2. For each fixed x between 0 and 2, y goes from 0 to the square root of 4 minus x squared. y equal to the square root of 4 minus x squared, that's x squared plus y squared equals 4. That's a circle of radius 2. So this is a circle of radius 2. And you remember that problem we had, I think problem 11, at some point where we were dealing with parts of circles. This is part of a circle. X is going from 0 to 2. Y is going from 0 to that circle. X squared plus y squared equals 4. Okay, so we're in the first quadrant, and we have 1/4 of a circle there. And so theta is going to go from 0 to pi halves in that first quadrant, that first part of that circle, and r goes from 0 to 2 because that's the radius of the circle. And then we're integrating e to the r squared. We have r dr d theta again in place of dy dx. So this is our dA. And now we can integrate this. You can see if I do a substitution, u equals r squared, the r dr is part of that derivative then for r squared is essentially there. So the substitution would be u equals r squared, du equals 2r dr. And then if I divide by 2, we can see r dr becomes 1/2 du. So this just becomes 1/2 du here. This becomes e to the u. So we're integrating e to the u du, and there's an extra 1/2. But we're just going to get 1/2 e to the u then, and u is r squared, so we're just going to get 1/2 e to the u, e to the r squared, where r goes from 0 to 2. Don't forget to plug in the 0 because e to the 0 is 1, but when we plug in the 2, we get e to the 4th power, so we have e to the 4th minus 1. And now we want to integrate with respect to theta. This is a constant, whatever e to the 4th minus 1 is. We can take that out. We're going to expect to theta, we just get theta evaluated from 0 to pi halves. So when theta goes from 0 to pi halves, that just gives us another pi halves. We have the 1/2 e to the 4th minus 1 times pi halves. That's giving me a 4 in the denominator and a pi in the numerator. So in this example, we're ending up with the double integral equal to e to the 4th minus 1 times pi over 4. And again, in order to do this, we had to switch to polar coordinates to evaluate this integral. And that finishes my lecture.